Today we'll briefly cover estimating population parameters. We'll also look at the basics of hypothesis testing, where we'll look at procedures for testing for a proportion and mean. And we'll look at testing for independence, where we'll use the chi-square test to test for association or independence. Okay, so the next part we are going to now look at estimating population parameters, right? And this topic introduces the concepts that are important in inferential statistics. It is the beginning of inferential statistics, right? So inferential statistics is basically where we use sample statistics, right? Sample data to estimate population parameters, right? So this is important. You have to pay attention at the terminology. Sample, statistic, population, parameter, right? So when you talk about a statistic, we are talking about a sample, right? And we talk about a parameter, we are talking about a population. Okay, so basically, this is inferential statistics is where we take from a population, right? From a population, we take a few individuals in that population, right? And then we study those individuals. So we'll take a few individuals, right? By a process of sampling, right? We take those individuals and then we study them, right? So we study those individuals, and whatever information we gather, right, from those individuals, we infer back to the population. In this particular course, you'll be expected to be able to estimate mean and proportion, right? So basically, it's easy. When you are estimating mean, it means that you are dealing with numerical data, right? You are dealing with quantitative data. When you estimate proportions, it means that you are dealing with categorical data, right? Categorical data. Here you'd be dealing with data like, let's say, blood pressure, weight, or level of income, right? Whereby the level of income is measured by the specific numerical data, right, in numbers. Where here, under proportion, you could still measure the level of income, but by using categories, right? Which means now that you are dealing with categorical data. In order to estimate population parameters using sample statistics, you need the point estimate, you need a standard error, and you need a confidence level. Okay, so the point estimate is basically taken from the sample itself, right? Let's say you sample from a certain population, and you are interested in, let's say, the number of people who drink alcohol, right? Or the proportion in a certain population that drink alcohol, and you find that you have, let's say, 40%, right? This 40% represents a point estimate and is taken from your sample. In order to infer this 40% to the population and say, okay, 40% of this population drink alcohol, then you need to construct a confidence interval. So the confidence interval, it gives you the estimate of the population parameter using the point estimate. The standard error is more or less akin to a standard deviation, right? But it applies to samples. For the proportion, the formula that we would use, that we'll look at in the next few slides, is, right, the standard error of proportion is equals to the square root of p hat times 1 minus p hat over n, right? So p hat represents the sample proportion, okay? So p hat is the sample proportion. 1 minus p hat is 1 minus the sample proportion. So this number is basically the number or the proportion within your sample who do not fall within the category of interest, right? So let's say you are measuring this 40% refers to the proportion who drink alcohol. It means that 1 minus p hat represents the proportion who do not drink alcohol, right? Other thing to note with this formula is you can work in percentage or you can choose to work in decimals. When you are working in decimals, then you'll have to use 1, right? When you are working in percentage, you'll have to convert this 1 to 100, right? Because otherwise it becomes 1 minus 40, right? And that doesn't make sense. So you'll have to convert this 1 into 100, where you'd now have 100 minus 40, right? Times 40 over whatever the sample size is, okay? The confidence level gives us what we call the multiplier. Most of the time the confidence level we'll use the 95% level of confidence, okay? And the multiplier that we use for this level of confidence is 1.96. That's the multiplier, okay? But of course, the multiplier will also change depending on whether you are using a t-distribution or a normal standard distribution. Again, keep that in mind when you work through questions. Now, for estimating mean, we basically go through the same procedure, right? We need a point estimate. In this case, the point estimate, right, will be the sample mean, right? And then the standard error is given by a different formula, of course. And the formula for the standard error of mean, right, is, so this is the standard error of mean, is given by the standard deviation, right, population standard deviation, over the square root of the sample size. Sometimes you don't have the population standard deviation and you have the sample standard deviation, right? Still, you can use the same formula, just replace the population standard deviation by S, which is the sample standard deviation. And if you are going to be using the sample standard deviation, right, that's when now you are forced to use the t-distribution, okay, when it comes to determining the multiplier. Okay, so this slide just highlights the formula that we use. So this is for standard error of mean, and this is for standard error of proportion. This symbol I said is called p hat, right? So this is proportion for a sample. You could have p, this is population proportion. So this is a parameter, this is a statistic, right? Same with mean, right? You know that x bar is sample mean, right? Mu is population mean. So this is population mean, which is a parameter. This is sample mean, which is a statistic. A center conducted a survey of 1,007 adults and found that 85% of adults, right, know what Twitter is, okay? The procedure now is to give an estimate of the proportion of adults who know about Twitter in this population at a confidence level of 95%. Okay, this is a typical question that you might get in an exam situation. Okay, so what you are supposed to realize here is, first of all, that you are dealing with proportion, not mean, right? That's one. Second, you are given the proportion as a percentage, right? So if you wanted, you could convert this formula, this one into 100, so that you can work with percentage. But what I prefer personally is to work with decimals. So I would usually convert this 85% into a decimal, which becomes 0.85. All right. Okay. So what do we know? So we are given the p hat, which is the sample proportion, is 0.85. We are given the sample size for this survey was 1,007. To use the formula, we need 1 minus p hat, right? By the way, 1 minus p hat, in some books, it's written as q hat. In this case, 1 minus p hat or q hat is equal to 1 minus 0.85, which is equals to 0.15. The other thing we are told here, okay, just to to keep in mind is that we are working at 95%, right? And because we are working with proportion, we know that we can use the multiplier of 1.96, right? 1.96. So remember, the formula itself says the confidence interval, right, is equals to proportion, right? So this is the sample proportion p hat, right, plus minus the multiplier times the standard error of proportion. In this case, is the standard error of proportion. Okay, so we have this, we have that. We have to calculate the standard error. Standard error, right, is equal to, so 0.85 times q hat, right, or 1 minus p hat, which is 0.15. Divide that by the sample size 1007, right? The top part would then become 0.1275, right? We divide that by 1007. So in the end, if you work through the problem, it will give you, if you use a calculator, it will give you 0.00012661, right? So this is what you'd have. So if you take the square root of this number, right, if you take the square root of this number, you get 0.0113, okay? Now that we have the standard error, we can apply the formula for the confidence interval, right? And now find the estimate for the population parameter. Okay, so P, which is the estimate now for the population parameter, is equals to, remember it says proportion, which is P hat, right, 0.85, okay, plus minus the multiplier, which is we said it's 1.96, the multiplier times the standard error of proportion, which is 0.0113. Okay, so this is basically what we have. And then this becomes 0.85 plus minus 0.0216, right? So this is 85%, right? Plus minus this as a percentage is 2.16, right? So basically this is what we have in percentages. So it means that the true population proportion lies somewhere between 85% minus 2.16. So 85 minus 2.16 is 82.8%. The upper limit is 85 plus 2.16%, which is 87.2%. So the population proportion, the true population proportion, lies somewhere between 82.8 and 87.2. Right, so now we are going to go through the basics of hypothesis testing, right? A hypothesis is basically a claim or a statement about a property of a population, right? It is, again, important to note that when we make hypotheses, we are making statements about a population, right? Not a sample, right? Not a sample. So a hypothesis test is a procedure for testing a claim about a property of a population, not a sample, okay? There are two types of hypotheses. We have the null hypothesis, right, which is the hypothesis of no difference, right? The hypothesis of no difference, right, the null. And then we have the alternative hypothesis, right? So this is the research hypothesis, right? This is the study hypothesis or the research hypothesis, okay? There are three ways to state the alternative hypothesis depending on what you are trying to establish, what you are testing. Whereas the null hypothesis is a statement of equality where we use the equal sign, right? The alternative hypothesis is a statement of inequality. Basically, we would say not equal to, or we'd say greater than, or less than, right? So these are the three ways in which we can state the alternative hypothesis. The other thing to be familiar with that we went through in the course is the probability value, or the p-value. So the p-value is used when we want to see how likely it is that a hypothesis is true, right? So this is the value that we use basically to test the hypothesis in the end. So it's a probability value. So it gives the probability of any observed difference having happened by chance, right? The probability that any observed difference occurred by chance. Or the other way is to say, it may sound redundant, but it is to say the chance that any observed difference happened by chance. Okay, that's basically what a probability value is, or a p-value is. Okay, and usually we would set our p-value at 0.05, right? The 0.05 will be a cutoff. So which means 0.05 is basically 5%, right? This is 5%. If the probability that any observed difference happened by chance is more than 5%, then we can conclude that indeed what we are seeing happened by chance. However, if the p-value is low, less than 5, we conclude that it's unlikely that what we are seeing happened by chance, which means that it is important. There is something behind what happened. It didn't happen by chance. The differences we are seeing are therefore important and significant. The steps: first of all, you set up the null hypothesis and the alternative hypothesis, right? You have your null hypothesis and your alternative, and then you determine the level of significance. Usually it will be given, right, as 0.05. That's the alpha level. And then you calculate your sample statistics, right? Sometimes, or most of the time, they will be given, right? You'll be given the sample size, the mean, or the standard deviations, or the proportions, right? So these are the sample statistics. So these are the numbers that we get from your sample. And then you use a formula, right? There is a formula that you may use depending on whether you are dealing with proportion or mean. So the formula will help you to convert this sample statistic, right, into a test statistic. Okay, and then we use the test statistic to find a p-value. To do that, we use a t-distribution or a normal standard distribution, depending on the situation. So for proportion, right, if you are testing a hypothesis for proportion, you will always need to use a standard normal distribution. For mean, it's different, right? Sometimes you need to use a t-distribution. So what are the situations in which you'll need a t-distribution? If the standard deviation, right, of the population is not known, right? Unknown standard deviation or unknown population standard deviation, then you use the t-distribution, okay? If the sample size is small, less than 30, then you use the t-distribution. You can see that this formula for finding the test statistic for mean are the same, right? This formula and this formula are basically the same. The only difference are the symbols, right? For standard deviation, if the standard deviation is, the population standard deviation is known, then we use the z distribution. And if we are working with a sample standard deviation, then we use the t distribution. So after you get your test statistic, the test statistic now is the one that will help you to find the p-value, right? And depending on the alternative hypothesis, you may need to double the p-value, right? You multiply the p-value by 2. The situations that you need to do that are when you are dealing with an alternative hypothesis which says not equal to, right? If your alternative hypothesis is the not equal to, then you need to double your p-value. Whatever p-value you get, you double it. So if the p-value is greater than, so if p-value, right, p-value is greater than 0.05, then we fail to reject the null hypothesis, right? Which means the null hypothesis stands. If the p-value is less than 0.05, right, then we reject the null hypothesis, which means the alternative stands. So that's that. So the way to remember this is that if the p-value is high, right, high, which is higher than 0.05, the null flies high, right? So the null hypothesis stands. If the p-value is low, right, which means it's lower than 0.05, then the null lies low. High p-value, null flies high. Low p-value, null lies low. Okay, so this is a t-distribution. This is how the t-distribution looks. So to use a t-distribution, you need to calculate degrees of freedom, right? And in order to do that, the formula is degrees of freedom is equals to n sample size minus 1. That will give you the degrees of freedom. Okay, so after you have the degrees of freedom, right, let's take for instance, let's say your sample size is 10. That means your degrees of freedom are 9. So you'll be dealing with this row, okay? After that, you determine your level of significance. If your alpha level, right, is 0.05, an alpha level of 0.05 means that you have 0.025 on each tail of the distribution. Okay, so it means that we are dealing with this here, right? So your t value will be 2.262, right? If you are dealing with degrees of freedom of 9 and a significance of 0.05. Be careful because some students get confused and they pick this column, right, of 0.05. But remember that you have to divide your alpha level into 2 because the t-distribution has 2 sides, right? The left side and the right side. Another way to remember this is just to look at the bottom of this particular table. So you can see it says here 95%, right? So it means that this is the one that corresponds to 0.05, right? Or 5%. If you were to pick this one, 0.05, this corresponds to 90%. So it's as if you are dealing with an alpha level of 10%. The average lifespan of a species of fish in Chobe River is 16 years. An environmentalist is concerned that contamination of the feeding grounds for this fish in his area has resulted in a shortened lifespan, right? That means that this researcher is claiming that the lifespan is lower, right, or it's way less than 16 years. Okay, so in order to prove his claim, he has recorded the ages of 25 fish. His sample shows a mean age of 13.2 with a standard deviation of 2.3, right? So we are dealing with a small sample size of less than 30 and a sample standard deviation. That means we are going to have to use the t-distribution. So test his claim of a shortened lifespan at the 0.05 level of significance. So our significance level is still the same, 0.05. Okay, so we set up the hypothesis. So the null hypothesis and the alternative hypothesis. The null hypothesis is that the mean value, right, the mean value mu, right, so this is the population the population mean is 16 years, right? That's what this says. The average is 16 years. And the alternative is that it has been shortened. So that means that the alternative says it's less than 16. That's it. So the second thing now to do is to determine the level of significance, which is the alpha level is 0.05. That's the level of significance. And the third step is to determine or calculate our sample statistics. So what are we given here? We are given a sample size of 25. We are given a sample mean of 13.2, right? And we are given a sample standard deviation, right, S of 2.3. So that's what we have for our sample. Okay, step 4 is to convert the sample statistic into a test statistic. So our formula for the test statistic is, right, T, it's a t-test. T is equals to x bar, which is the mean of the sample, right, minus mu population mean. We divide that by the standard deviation divided by the square root of the sample size. Okay, so this becomes, it's easy, 13.2 minus the population mean, which is 16, divide that by 2.3, which is the standard deviation, over the sample size, which is 25, right? So this gives us 2.8 divided by 2.3 over 5, right? So the square root of 25 is 5. So this becomes minus 2.8 over 0.46. So the final answer is minus 6.087. So that's our T, right? That's our test statistic. So our test statistic is 6, so minus 6.087. Okay? So there are two ways to do this. One way to determine the p-value, right? That's step number 5. P-value is equals to, and the other way is to find the critical value, is the critical value method. Critical value. I will discuss both ways. So let's look at the p-value. So remember that in order to use the t-distribution, we need degrees of freedom. So the degrees of freedom are given by n minus 1. In this case, our n minus 1 is, our sample size n is 25 minus 1 is 24, right? So our degrees of freedom are 24. So let's go to the t-distribution table. Right, so this is the t-distribution table that we discussed earlier. So our degrees of freedom are here, right? 25 minus 1, which gave us 24, right? And the p-value at a test value of minus 6.087 would be way out there, right? So remember that these values, although they are positives, can also be used as negatives. This table only lists positive values, but you can also turn this into negative. So for instance, this 3.7454 also represents negative 3.7454. So this is plus minus. All of these numbers are sort of plus minus. Okay, so the p-value at degree of freedom of 24 and a test value of minus 6.087 would be way less than 0.05, right? You can see that we have 0.0005 there, right? So that's the smallest p-value that we have, right? And this p-value corresponds to a test value of 3.7454. And remember that our test value is 6.087, right? That means it's way off the chart this way, which means that the p-value, right, if we are using the p-value method, our p-value is going to be way less, right? P-value is going to be way less than 0.0005. This is what this means, and therefore we would reject the null hypothesis using this p-value because the p-value is way small. So the other method is to use the critical value method. For the critical value method, what basically we are saying is at degrees of freedom of 24, our critical value, right, at a level of significance of 0.05 is going to be this one here, right? And the reason why we pick 2.06 is because remember the t-distribution has two ends, right? So if our alpha level is 0.05, we have 0.025 on this end, right? And on the other end, we have 0.025. Together, it makes 0.05. Okay, so we are using this number here, right? We are using this number here in order to determine the critical value. The critical value here is 2.06. If the critical value is 2.06, it means that, right, it means that we have 2.06 here and we have negative 2.06 this side. And remember that our test, right, our test value is negative 6.087, which is way out here in the rejection zones, right? Since our test value is way out of the way out in the critical zones, in the rejection zones, right? This is the zone of acceptance. This is where we would fail to reject the null hypothesis. Outside of this zone, we would reject the null hypothesis, right? So we reject the null hypothesis again by using the critical value method, just the same as we did by using the p-value method. Our conclusion means that we are going to, we said to reject the null hypothesis, which means there is sufficient evidence to suggest that the mean age, right, of this species of fish is less than 16 years old, right? Or there is no sufficient evidence to suggest that it's equal to 16, okay? Which means the claim of this environmentalist is correct, that the mean age is less than 16, right? But we are not saying it's equal to 13.2, right? The conclusion would be it's less than 16 because that's what the alternative says. Okay, so the last bit that we are going to do here is testing for independence, right? So to do this, again, in your notes, you can go through the detailed notes where we use the Pearson chi-square test. The Pearson chi-square test is a test of independence, right? So it tests the null hypothesis that in a contingency table, the row and the column variables are independent, right? This will make sense once we go through an example. So it measures the difference between actual and expected frequencies, right? And helps us understand the relationship between two categorical variables, right? Important to note that we are dealing with categorical variables when we perform a chi-square test, okay? Just like for any other hypothesis testing, we need the null and the alternative. So the null hypothesis would say that the two variables, right, the row and the column variables on the contingency table are independent. This means that there is no association. And the alternative would say the row and the column variables are dependent, which means association. Okay? So in order to calculate the chi-square, we use this formula. So this is how the distribution itself looks, and I'm sure you are familiar with it. And it's very similar to a t-distribution where we have the degrees of freedom and we have our p-values, and of course we have the critical values or the areas listed, right? So in order to use the table again, we need degrees of freedom, and to calculate degrees of freedom for this, it's a bit different from how we did it with the t-distribution. Here we take into consideration the rows and the columns, and the degrees of freedom formula says the row, right, the number of rows minus 1 times the number of columns minus 1. That's the degrees of freedom when you are using the chi-square distribution. Okay, so we have a question here which says, is there an association between smoking status and gender? Use the chi-square test for independence to determine this fact, right? State your null and alternative hypothesis. So basically, we are asking if on this particular table here, is there an association, right, between gender, which is one category, gender, and smoking status, right? So does gender determine smoking status? Is smoking status linked in any way to gender? Is there an association? So we test for independence. So the null hypothesis would say there is no association, right? And the alternative would say there is an association. To run the chi-square test, we need another 2 by 2. So this is the observed, right? So this is the observed. This is observed. This is what was observed on the sample, right? And this is what would be expected if there is no association, right? So in order to calculate the expected values, remember the formula says in order to calculate the expected, you take the row total, you multiply it by the column total, and divide by the grand total. Row total times column total divided by the grand total. So this formula gives you the expected value, right, for each cell. Let's first of all fill in the totals here. So the total here is, this is 25, right? The total here is, this is 1131. The total here is 30. The grand total is 61, right? The total here would be, this is 17 plus 19. It gives us 36. These are the totals. So these are the row totals, okay, and these are the column totals. This is the grand total. So, and these are the observed values. So in order to find the expected value here, we would take the row total for this, which is this one, right? This is the row total. So it's 25 times the column total, which is 31. Divide that by the grand total, which is 61. We get 12.705, right? So if you do that for all the cells, right, this is 12.705. You do that for all the cells, here you would get 12.295. Here you would get 17.705. And on this cell you'd get 18.295, right? So this is what was observed. This is what is expected if there is no association, right? To apply the formula for calculating the chi-square, remember it says chi-squared is equals to the sum, right, of the observed frequencies minus the expected frequencies squared over the expected, right? Which means we are going to calculate all of this, right, and then sum. That will be our chi-square. To do that, I usually expect students or advise students to construct a simple table such as this one, right, where here you would have the observed value, one column you have the expected frequency, then the other one you have expected minus observed minus expected, and then the final one you have observed minus expected squared over expected, right? And then in the end you have total, right? At the bottom you would have the total. Okay, so if you do that, you'll find that you are unlikely to make a lot of mistakes, right? You'll have your totals there. Okay, so which means your chi-square should appear here, right, where you have done everything, you have done the entire procedure, and you have added, you have summed the observation minus expected squared over expected. You find the sum, and this would be your chi-square, right? So let's do that. So for our observed frequencies, we have 14, right? 14, our expected is 12.705 right here, right? So 12.705. Our observed minus expected. So this minus this is 1.295, right? And then our observed minus expected squared. So we take this, we square it, and then we divide by expected. That number is 0.131. So you do the same for all the cells. And if you do that correctly, this is what you will have in the end. So the totals here, we have 61. Here we have 61 as well. Here we have 0, right? And the total for this column gives us our chi-square, and it's 0.452. So that's our chi-square. This is our chi-square, this number there. So we use this number now to determine whether or not there is an association between our variables, right? So our chi-squared is 0.452. Our degrees of freedom, right? So degrees of freedom is equals to the number of rows, right? Which is 2 minus 1 times the number of columns, which is 2 minus 1, which is equals to 1, right? So our degrees of freedom are 1. We'll be working with this part here, right? And our chi-square is 0.452, right? Where is 0.452 in this row, right? It's somewhere here, right? So we can estimate that our p-value is somewhere between 0.75 and 0.50. Our p-value is somewhere between 0.75 and 0.50, right? It's a high p-value, so the null flies high, right? Which means that there is no sufficient evidence to reject the claim that there is no association, right, between gender and smoking status, right? So we fail to reject the null hypothesis, and the conclusion will be there is sufficient evidence to conclude that smoking status is independent of gender, right? Or in this particular data, whether someone smokes or not is not associated with their gender. So gender and smoking status are not associated in this particular instance, right? So that's using the p-value. We can, if we choose, use the critical value, right? In order to use the critical value, this is what we'd have, right? For degrees of freedom of 1, right? Degrees of freedom of 1, our critical value, right, at 0.05, our critical value is 3.84, right? Which means anything outside of this would be in the rejection zone, okay? So, and we calculated our chi-square to be 0, right? Our chi-square to be 0.452, right? So 0.452 is on this side, right? On the non-rejection side, right? So 0.452 would be somewhere there. So that means that even when you apply the critical value method, you still end up with the same conclusion, right? That there is insufficient evidence to reject the null hypothesis, which means that smoking or smoking status and gender are independent, are not associated. There's no association between those two variables in this particular instance. Okay, so thank you for listening, and I hope this helps. If you think this was useful, subscribe and share the video. If you have any comments, leave them in the comment section below.